So the first video in this module was all about figuring out what type of reaction was occurring based on being given a complete chemical reaction. But the reason we really need to know what kind of chemical reaction is happening is so we can take two compounds or an element in a compound and predict what's going to happen when you react them together. So that's what this video is all about, is predicting what kind of products we're going to get out of a reaction. The first type of reaction that you're going to have to predict is the easiest, which is why we're starting with this one. And we touched on this one a little bit more for prediction purposes in the first video because the products are always going to be the same. If you're looking at a combustion reaction, for the sake of this class at least, combustion reactions, remember, are always going to be hydrocarbons, C's and H's, sometimes with O's, plus oxygen, which has to be O2 because oxygen is diatomic. It's always going to make carbon dioxide and water for the purposes of this class. So anytime we have a hydrocarbon like C6H14 and we add oxygen, O2, what we're going to get is CO2 plus H2O. Doesn't matter what your formulas are, you're going to get CO2 and H2O. Then you'd have to go back and balance it like we talked about in 6.2, but for right now, we just need to predict our products, CO2 and H2O. Same thing if we've got something like C3H6O, still counts as a hydrocarbon because it's just C's and H's plus an oxygen. Then we add oxygen gas, and we're still going to get CO2 plus H2O. These are the products for complete combustion. Remember, you're used to seeing combustion reactions. You saw one back when you were in biology, because remember, photosynthesis, cellular respiration also counts as a combustion reaction. Photosynthesis is backwards. But not all the combustion in the world is going to be complete combustion. In real life, if you've got a hydrocarbon plus not enough oxygen, you can get carbon monoxide, which remember is going to just be CO. Or you could just get C, which is soot. So if you've ever burned something over a campfire and gotten all that black on it, that's just carbon by itself. That means you're not burning enough oxygen. This also, remember, is why you shouldn't burn things like charcoal in your house, because if there's not enough oxygen provided, you get carbon monoxide, which is poisonous. Alright, so our next type of reaction is going to be a little more complicated to predict. Our double replacement reactions. You're going to have two ionic compounds reacting together. They're going to trade partners. And remember, opposite charges attract, like charges repel. So you've got to end up with a cation and an anion in each product. You can't end up with two cations together or two anions together. And you have to have legitimate chemical formulas for all your products. So you've got to take our charges and cross them still. Alright, so let's look at our first one. We have sodium chloride plus silver nitrate. So we want to take a cation from one and an anion from the other. So we're going to take our sodium and our nitrate. And remember, Na has a +1 charge, and NO3 has a -1 charge. So one of our products is going to be NaNO3. We've used that part. That leaves us with silver and chloride. And we remember that both of those also have +1, -1 charge. So that's going to be AgCl. And we'll learn later in the year what actually happens when that one happens. This is going to be a precipitation reaction, we'll find out later, because silver chloride isn't soluble in water, but we'll talk about how to figure that part out more later. Alright, this next one is going to look a little weird because there's not a metal in our first one. We have hydrochloric acid plus sodium hydroxide, but it's going to be the same thing. You're going to take your cation from your first, so your positively charged ion in your first is going to be your H. It's going to react with the anion in your second, which is your OH. And so we're going to end up with HOH, which we could also write as H2O. Sorry, we're going to box our answer from up here. We could also write as H2O plus That leaves us with Na and Cl, and that's going to be our product for our second. This, by the way, is a special type of double replacement reaction called a neutralization reaction, which we'll talk about a whole lot more once we get up to acids and bases. But we've got H pairing with OH, we've got the cation from our second compound going with the anion from our acid. And again, we'll talk about this more later. All right, this next one is the first one we're going to have to look at crossing our charges. We've got iron sulfide plus hydrochloric acid. And we know from experience that iron can actually have more than one charge. But we know that sulfide always comes with a -2. So our iron in this case has to be a +2. And that iron has to pair up with something from our second. It's a little less obvious because, again, one of them is an acid, so we've got H as our cation, but we've got to have Cl as our anion, so our iron and our Cl are going to come together. We have a Cl with a -1 charge. What do we do with our charges? We've got to cross them. So we're going to bring our charges down. So our first product is going to be FeCl2 plus, that gets rid of our Fe and our Cl, that leaves us with H and S. We just said that S comes with a -2, H we know comes with a +1, so we're going to have, then our second is going to be H2S. And again, I'm not balancing any of these. This one we would have to balance yet, but I trust you guys to be able to do that. So we're going to end up with FeCl2 and H2S. Alright, now our last type of reaction prediction gets a little more complicated. In a single replacement reaction, we remember from our first video in this module that you have a single element kicking something out of a compound and so something from that compound becomes a single element. You have an element plus a compound gives you an element plus a compound. What we have to worry about when we're doing single replacement reactions is whether or not that can actually happen. You need a more active pure element to replace a less active element that's part of a compound. If you've got a metal, it's going to replace the metal or the hydrogen in the compound. If you've got a non-metal, it's going to replace the non-metal. Same thing like we talked about in double replacement reactions. You shouldn't be ending up with two metals together. It doesn't work out. If the pure element is less active than whatever was in the compound, there's not a reaction. Now, I'm sure you're sitting there asking yourself, how do I know whether something is more or less active? This is where the activity series comes in. And you've got a very similar list to this on the back of your periodic table, the same place you've got your list of polyatomic ions. They just list the names out instead of listing the elements. So anything high on the list, these are going to be your most active elements. Whatever's highest on the list wants to be in a compound. So no matter what, lithium would rather be in a compound. The reaction's going to happen so that's true. If lithium's already in the compound, it's just going to stay there. You're not going to have a reaction. If it's lower on the list, it's less active. That would rather be a pure element. So, high on the list, wants to be in the compound. Low on the list, would rather be a pure element or is okay with being a pure element. Looking at your activity series is how you're going to determine whether or not a single replacement reaction will happen. Nice thing is then if it doesn't happen, you can just write no reaction and move on. Alright, so you've got your list of metals. I understand there's not a whole lot of rhyme or reason to your list of metals. I don't expect you to memorize your list of metals. If you notice, though, on your nonmetals, the only nonmetals we worry about are our halogens. And halogens just go in the same order as the periodic table. So fluorine at the top of the periodic table is the most active. Iodine's the least active. So iodine's okay with being a pure element. Fluorine really, really wants to be in a compound. So just look at the order on the periodic table for that one. Nothing fancy on that. All right, let's look at some actual examples of this. So, single replacement reaction. We've got our single element, copper. We've got our metal in a compound, silver. We've got to go back and look at our activity series. So, copper is currently our single element. silver is in our compound. We look at our notes here, we say that higher on the list prefers to be in a compound, lower on the list prefers to be single. Right now the single one is higher, so the reaction's going to happen. So what's going to happen is our copper is going to kick out our silver, and silver is going to be by itself. So we're going to end up with just Ag, and then we're going to end up with copper nitrate. And this one's a little bit, you're going to have to watch out with your transition metals. It is a little hard to predict what charge your transition metal is going to have. Typically, you're best off assuming your transition metal is going to have a +2 charge. So if copper's got a +2, we know that nitrate comes with a -1. So you're going to need 2 nitrates because we crossed our charges. +2, -1, we have 1 copper, 2 nitrates. That one, it's not the end of the world if you end up not switching the charges right. Well, it is the end of the world if you end up switching the charges wrong. If you choose to go with +1 copper, it's not the end of the world. Alright, zinc and hydrochloric acid. Let's go back to our list again. Do a little erasing. Okay, so this time around, our single element is zinc. Hydrogen is part of our compound. And you'll notice the note at the bottom, activity series is based on hydrogen standard. We understand that hydrogen is not a metal, but it's a good reference point for a lot of things. So, our pure element is higher on the list. It wants to be in the compound, so whatever's higher on the list replaces what's lower on the list. So, what's going to happen here is our hydrogen gets kicked out. And we know hydrogen is one of our 7 diatomic elements. So we're going to get H2 plus, we've got a pair of zinc with Cl. And we know that zinc is one of our transition metals that always comes with the same charge. Zinc's always going to be a +2. Cl always has to be a -1. So we cross our charges. So H2 plus ZnCl2. Alright. So zinc and hydrochloric acid gives us hydrogen gas and zinc chloride. Alright, our next one we have sodium chloride and iron. So we've got to compare our 2 metals on our list. So we go back. Sodium is currently in our compound, and iron is a pure element. So, is anything going to happen? No, because if it's higher on the list, it would rather be in a compound. Sodium is higher on the list, and it's already in a compound. So all we've got to write here is no reaction, or NR. Nothing's going to happen. You can't get pure sodium out of salt by adding iron to it. You'd have to add something higher on the list than sodium, and there's not a whole lot. Alright, our next one. This is our first one where we're adding a halogen to a compound. So we've got magnesium bromide and chlorine gas. So now we've got to go back and look at the other part of the list. Remember, we can also look at the periodic table for this one. So we go back over here, and it's magnesium bromide, so that bromine is in our compound. Chlorine's our pure element. So chlorine's our element. That's in our compound. Alright, so our pure element is currently higher than our compound. So higher on the list means it wants to be in a compound. So this is actually going to happen. Our chlorine's going to kick out our bromine. So we end up with MgCl2 plus Br2. So remember, Cl2 and Br2 out as pure elements have to have the 2 because they're diatomic. With the Mg, the reason there's the 2 there is because magnesium has a +2 charge, and chlorine and bromine both have a -1 charge. If you look at one like the next one, you're not always going to have a 2 with the halogen in the compound. There we've got Kf, potassium fluoride, plus iodine. So go back, we look at our list, and we see that fluorine is higher than iodine, which means this one's not going to happen either. Okay? But if it did happen, we'd end up with Ki, not Ki2, because K's got a +1 charge. Watch out for your charges. Make sure you're writing your formulas correctly. All right. Now, we want to look at some examples. We would have to figure out what type of reaction we're doing first, because that's going to help us predict our products. And then we're going to have to predict the actual products. So our first one, we've got a pure element plus a compound, which means it's got to be a single replacement reaction. So we're going to have to look at our activity series. So if you look at your activity series, you'll notice, and I'm going to flip back for a sec, you will notice that sodium is higher than magnesium, which means this will happen. Watch your charges though, because Na comes with a +1 charge, oxygen comes with a -2, so we need 2 sodiums for every 1 oxygen, plus magnesium metal. You're not going to have any charge on your pure element. It's just by itself. All right, our next one, we've got a compound, K2SO4, plus another compound, iron nitrate. So we've got to do a double replacement reaction. So we're going to switch partners. So our K from our first compound is going to go with our NO3 from our second. And remember, those subscripts are all coming from crossing your charges. So we know K comes with a +1. We know NO3 comes with a -1. So our first product is going to be KNO3 plus, we've got to cross our charges for a second. If it took us 3 nitrates, we know we've got Fe +3. And then we've got SO4, which we know sulfate always comes with a -2. So we're going to have to cross our charges. Okay, so we're going to have Fe2SO4 3. And remember, our parentheses are just telling us we've got 3 of all of SO4. We don't have 43 oxygens. That would be bad. All right, so now we've got bromine plus sodium chloride. And we know, let me get this out of our way, we know from looking at the periodic table, because the activity series for halogens is the same as on the periodic table, that bromine is lower down than chlorine. And lower down means it's okay with being an element. So this one is nice and easy, actually. It's no reaction. And remember, it was a single replacement reaction because it's a pure element plus a compound. All right, so this next one, if you just glance at it quickly, it's going to kind of look like it should be a single replacement reaction. But we know it's a special one because it's a hydrocarbon, C2H6, plus oxygen gas. And we know hydrocarbon plus oxygen means something's on fire. It's a combustion reaction. Always has the same products. It's always going to be CO2 plus H2O. Later on, I'll make you figure out whether you've got enough oxygen or not, whether other things could happen. All right, next one down, we've got 2 compounds again, because we've got way too many letters for anything else. Remember, this is our one that's going to look weird, because we've got H and OH as our first cation anion to pair together. So it's going to be HOH, which you could rewrite as H2O, it's just water, plus, you want the rest of it to come together. We know Ca comes with a +2 charge. We know PO4 comes with a -3. We're going to cross our charges. And we end up with Ca3 PO4 2 when we cross. So, calcium phosphate. All right. And last but not least, we have an element plus we have a compound. And we know element plus compound is single replacement. And single replacement, we're going to have to go back and look at our activity series. Got to figure out whether strontium or hydrogen is higher. So, try and clear some of this out. Strontium is up here. Hydrogen's way down here, so strontium does want to replace hydrogen. So strontium's going to end up with our NO3, but strontium, we remember, when it becomes part of a compound, is going to have a +2 charge. NO3 always has a -1, so we're going to cross our charges. So we're going to end up with SrNO3 2 plus our single element, because we've used our strontium, we've used our nitrate. We're just going to leave H by itself, but H is never just by itself. It's a diatomic element, so it's got to be H2. Alright, so just keep in mind, metals swap with metals, nonmetals swap with nonmetals. That works for both single replacement and double replacement. You've got to make sure that you're keeping legitimate ionic compounds. We're only making covalent compounds if we're doing combustion, and the only thing we're going to get out of combustion is CO2 and H2O. Alright, pay close attention to what you're doing. Try these on your own. Make sure you're following your activity series for any of your single replacements. For right now, we're going to assume all our double replacements actually happen. Alright, so make sure you got everything down in your notes. Work on your practice. Make sure that you ask questions if you've got them.